Hello, this is Dr. Oz. Today I would like to talk about integer linear optimization models. And these models are called integer and also linear because the functions are linear. However, at least there's one variable in these models that are integer. Okay? So these models, again, as I told you, at least one or more variables have to be integer, otherwise we cannot call it integer linear programming. So let's talk about types of integer linear optimization models. So there are different types. One is all integer linear program, which means that all my variables are integer. Second is LP relaxation. Basically, I can relax my problem so that I can solve a linear version of my program, and that will give me a upper or lower bound depending on maximization or minimization problem. Mixed integer linear program. Some of those variables are integer, not all. And then binary uh, integer linear program. Basically, my variables can get the values of 0 or 1. So let's talk about an example, at Eastborne Realty, which is an integer optimization problem. And I would like to first, in this video, talk about geometry of linear optimization problem. So in this problem, there is a company, Eastborne Realty, has $2 million to purchase um, rental property. And after initial screening, Eastborne company decides try to decide between townhouses versus apartment buildings. So each townhouse on average costs us $282,000, and there are only 5 available for us to purchase. And each apartment building costs us $400,000. Looks like we can buy as many as we want in terms of apartment buildings. So in this case, we will hire a property management company, and property management company has 140 hours available for us in terms of our contract. And on average, based on historical data, we know that each townhouse will expect to require 4 hours per month, versus apartment complex is bigger and more problem sounds like 40 hours per month per apartment building. So the profitability of townhouse is $10,000 per townhouse, um, and for apartment building is $15,000 per apartment. Let's say these are per year. So now, as an owner, we would like to decide how many townhouses and how many apartment buildings we should purchase. So that's the decision that we would like to make. So let's define our decision variables. We define 2 decision variables, T and A. T is number of townhouses purchased. A is number of apartment buildings. So our objective function, this is a maximization problem. Maximize the profit, which is $10,000 for every T townhouses plus $15,000 annually for every single apartment complex that we bought. We have 3 constraints in this problem. One is funds available. We don't have infinite budget, and we have $2 million. It's our right-hand side value, less than or equal to the amount of money that we spent. So every townhouse will cost us $282,000, 282K, times number of townhouses, T, plus $400,000 per apartment complex, so times A, 400K A and 282K T. When I add these numbers, it should be less than or equal to $2 million. Another constraint we have here is manager's time constraint. And these are in hours. So we know that our management company has up to 140 hours. So every single townhouse, 4T, takes 4 hours, and every apartment building on average costs us time-wise 40 hours times 8. And we have townhouse availability constraint. And we know that the right-hand side value is 5 townhouses because that's the maximum number of townhouses that we have. All right, so these are the 3 constraints that we have in this model. And we also have variables T and A, right, that we talked about. T and A must be non-negative, because these values cannot be negative. I cannot buy negative number of apartments. And also, we know that T and A must be integer, because I cannot buy a part of half a townhouse or apartment. Right. So this is our model. We talked about the objective and constraints. If I write them all together here in next slide, we are trying to again maximize our objective, which is 10T, $10,000, 15A, subject to $282,000 for every single townhouse, plus 400 for apartment complex, less than or equal to 2,000. All numbers are in thousands in this constraint. And also 4T has to plus 40A should be less than or equal to 140 hours. And T has to be less than or equal to 5. And T and A should be greater than or equal to 0 and integer. So this is called a linear all integer program. All integer program. As the variables are, as you see, the relationships here are linear functions. These are all linear functions. However, the values of those decision variables are integers. So if you look at the graphical representation of this problem, here's our manager's time constraint. And it's less than or equal to constraint, so it should be less than this line. And here is our available funds constraint. This red one right here. Again, it's a less than or equal to constraint, so it has to be less than or equal to so under this line. And we have number of townhouses available constraint, which is right here. I'll just use a different color. Again, it's a less than or equal to constraint, so everything here will be a feasible area. So when we highlight this area under this curve, under these 3 lines, basically we will get the area right here. And we know that our area is surrounded by non-negativity constraints, so that's why it cannot be less than 0. So in this feasible area, as you see here, the optimal solution, if you do linear relaxation, would be B, because this is my objective function, which is the black line. If I move this one outwards to maximize my problem, it will leave my feasible region by the point B, which is the best solution if this was a linear program, LP. However, we know that it's not a linear program. This is integer variables. So a linear program would give us this result. By 2.479 townhouses and by 3.252 apartments, which would end up $73,574. But this is a LP relaxation. So I know my best solution for integer program should be less than or equal to this, because this is a upper bound for me. And all the feasible solutions for this problem is these dots. As you see, this is a solution, possible solution, feasible solution, feasible solution, feasible, 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 feasible solution for here, feasible solution here, and so on. So we need to find the best solution for this. And so here are the answers for this problem. And if I run these numbers up or down, my costs will change significantly, because I know that each townhouse is $282,000 and each apartment is $400,000. So if I run these numbers to find a feasible solution, it will make a big difference. All right. So let me just show you how much of difference we will have. For example, if I run these numbers to 2 and 3, 2 townhouses and 3 apartments, then my new solution will be 65,000 instead of 73,000, and this is roughly over 10% decrease. So this is pretty bad. There's a big difference between 73,000 versus 65,000. All right, so let's take a look at the next page. So what's the cost of this model? I think this slide is wrong, because if I multiply 282 times 3, that would give me 4. So I have 268, $846,000 plus $1.2 million. If I add it up, this will give me around, this number is wrong, $2,046,000. So that's the cost that we are talking about, 2.46. So we are short by $46,000. So this is not a feasible solution. Of course, if we borrow money, $46,000 from someone somehow, this solution will be feasible. But at the moment, $246,000 is greater than 2 million. So that's why this is an infeasible solution. All right, so next video, I will solve this problem using Excel Solver. Until next video, enjoy business analytics.